equilibrium state between the ions and the undissociated molecules in solution. So it is the equilibrium state that involve ions and undissociated molecules in solutions. So this is what we say ionic equilibrium. Now remember it's a physical process. Dissociation, or you say ionization, this is a physical process. So it is a physical equilibrium. As you know that if we increase the temperature, the dissociation will increase and the equilibrium will shift in the right direction, forward direction, and that means the equilibrium will be disturbed. And if you make the temperature constant, it will attain a new equilibrium. So let us see an example of ionic equilibrium. You know that water is a very, very weak electrolyte. Water is a very, very weak electrolyte. You know it. So water, it dissociates into hydrogen ion. It is written as hydronium ion, hydrogen ion, and hydroxyl ion. Hydronium ion and hydroxyl ions. So this is the ionization of water. Water is a very weak electrolyte, therefore it dissociates very, very feebly and giving hydronium ion and hydroxyl ion. These ions are in small quantities and water molecules are in large quantities. So this is an equilibrium between ions and undissociated molecules. Undissociated molecules. So this equilibrium is called ionic equilibrium. Equilibrium involving ions and undissociated molecules at a given temperature is known as ionic equilibrium, since water is a weak electrolyte. If we talk about strong electrolyte, say for example KCl, if you take a solution of KCl solution, KCl will be fully ionized into K plus at once and Cl minus at once because it is a strong electrolyte. Therefore, there is no question of attainment of equilibrium because KCl, the entire KCl units will be dissociated into K plus and Cl minus. So there will be no equilibrium system. It is unidirectional. The entire molecules, entire units will be dissociated into K plus and Cl minus. So if we talk about KCl solution contains only K plus ions and Cl minus ions. There will be no KCl units undissociated. Why? Because it is a strong electrolyte. Strong electrolyte is supposed to be nearly 100% dissociated. So this dissociation is 100%. It is 100% or almost 100% dissociated. That means its degree of dissociation is unity. Degree of dissociation, that is denoted by alpha, is unity, 1. That means alpha is 1 means 100% dissociated. Alpha is the number of molecules dissociated by the number of molecules taken. So 1 means all the molecules of the electrolyte have been dissociated. That's why alpha is 1, means 100% dissociated. But in case of weak electrolyte, because ions and undissociated molecules both exist together in the solution, therefore an equilibrium is set up between the undissociated molecules and ions. And in these cases, weak electrolytes, alpha is very, very less than 1. This is, you will find, alpha is very, very less than 1. So we have two types of electrolytes. Weak electrolytes like HCl, H3PO4, H2CO3, acetic acid, other organic acids, ammonium hydroxide, copper hydroxide, etc. These are weak electrolytes. But this means their alpha is very, very less than 1. And strong electrolytes, example KCl, NaOH, HCl, HNO3, sulfuric acid, potassium nitrate, these are strong electrolyte, means their dissociation is almost 100%. So equilibrium, ionic equilibrium is attained only in case of weak electrolyte. Ionic equilibrium cannot be attained in case of strong electrolyte. Remember, this is the point. You understand that weak electrolytes can attain ionic equilibrium. Strong electrolytes can't attain ionic equilibrium. Now, why it is so? Because undissociated molecules and ions both will exist in the solution in case of weak electrolytes. However, in case of strong electrolytes, only ions are present. There will be no undissociated molecules or units. That's why no equilibrium is attained in the second case, that is for strong electrolytes. Now see the dissociation of water. This is how we have written the dissociation of water. Water is a very, very weak electrolyte. So at 25 degrees centigrade, this is a standard temperature taken, and the concentration of hydronium ion is measured, and it is 10 to the power minus 7 molar, and concentration of hydroxyl ion measured, it is 10 to the power minus 7 molar. So in case of water, the hydronium ion concentration and hydroxyl ion concentrations both are equal at 25 degrees centigrade. This is their values. Okay. Therefore, hydronium ion and hydroxyl ion, their concentrations are equal. In salt, we are writing in this way: hydronium ion equals to hydroxyl ion. These concentrations are equal. The solution will behave like a neutral solution. If hydronium ion concentration is greater than hydroxyl ion concentration, the solution will behave acidic in nature. And when hydronium ion concentration is less than hydroxyl ion concentration, the solution will show basic nature. So regarding this, you see the condition when both ions, their concentrations are equal, the solution is neutral in nature. When hydronium ion concentration is greater than hydroxyl ion concentration, the solution will show acidic nature, and when hydronium ion concentration is less than hydroxyl ion concentration, the solution will show basic nature. Now, as because this is an equilibrium system, every equilibrium system is characterized by an equilibrium constant. So let us write down the equilibrium constant K for this reaction, K for this process. K equals to hydronium ion concentration multiplied by hydroxyl ion concentration divided by concentration of water power 2. As we know, water is a pure liquid. Therefore, this is a constant term. This constant term is multiplied with K. K is constant, and this is also constant. Therefore, this constant and this constant multiplied, and the resulting constant is denoted by Kw. Kw is equal to Kw. Kw is equals to hydronium ion concentration multiplied by hydroxyl ion concentration. So see, this is called ionic product of water. This equilibrium constant is known as ionic product of water. So ionic product of water is hydronium ion concentration multiplied by hydroxyl ion concentration. That is the product of the concentration of its ions of water. That is ionic product of water. At 25 degrees centigrade, hydronium ion concentration 10 to the power minus 7, hydroxyl ion concentration 10 to the power minus 7. Therefore, if you put their values, the value of Kw will be 10 to the power minus 14 at 25 degrees centigrade temperature. The value of Kw equals to 10 to the power minus 14 at 25 degrees centigrade temperature. Because if you increase the temperature, this value will increase. If you decrease the temperature, this value will decrease. Because if you increase the temperature, the ionization will increase. If you decrease the temperature, the ionization will decrease. That's why the Kw value depends on temperature. Every equilibrium constant, their values depend upon temperature. So at a given temperature, we are talking it. Now see, I am Kw, both sides we are taking negative logarithm of hydronium ion concentration into hydroxyl ion concentration See here, we have taken negative log to both sides. Now this is denoted by pKw. So what is P? P is the negative logarithm. Of Kw. So pKw. Now you know that log A to B equals to log A plus B. Log A to B equals to log A plus B. Since there is a negative sign, so we are writing negative log H3O plus minus negative log, or you can write it this way, plus then minus negative log of hydroxyl ion concentration. See here. This is the expression of log A to B equals to log A plus log B. Clear? Negative sign is there, so we have written negative here, we have written negative here. Again we will see that pKw, this is equal to negative log is P, it is a scale. pH it is written. pH means negative logarithm of hydrogen ion concentration, and this is written plus POH. POH means negative logarithm of hydroxyl ion concentration. So pKw equals to pH plus POH. Remember, pKw it is in negative log. If you write it, expand it, it is minus log Kw equals to minus log H plus concentration minus log OH minus concentration. So what is pH? pH can be written this way. pH equals to minus log of hydrogen ion concentration. Since hydrogen ion exists in the form of hydronium ion, that's why we are writing H3O plus. Okay. Now see again, Kw equals to 10 to the power minus 14. So if you write this one further, so 10 to the power minus 14 minus log Kw equals to minus log 10 to the power minus 14 minus log 10 to the power minus 14. This is equal to minus into minus 14, this is equal to 14. 14 log 10 is 1. So pKw equals to pH plus POH equals to 14. If you take this value, the value of Kw here, so if you take negative log of this, you will also take negative log of this. So negative logarithm of 10 to the power minus 14, this is equal to 14. This is a simply application of log. So we come to know that pKw equals to 14 and pH plus POH is also equal to 14. This is not only for water, this is for any solution in aqueous medium. Since it is an equilibrium system, water dissociates as H plus and OH minus. If you add acid to it, the equilibrium will be adjusted according to Leach-Atelier's principle. If you add acid, the process will go in the backward direction, okay, and will maintain the value of Kw. If you add base to the solution, means if you make the solution basic, the hydroxyl ions are added to water. That means the dissociation of water will be moved to the backward direction in order to maintain the value of Kw. So Kw is equal to 10 to the power minus 14, or you can say pKw equals to 14. This value is valid for any solution, whether it is neutral, acidic or basic. Remember it. You can apply this relation for any solution which is neutral or acidic or basic. That means for any type of aqueous solution. Now see, we are explaining it with the help of an example. We are explaining it with the help of an example. This is the dissociation of water. Dissociation of water is plus OH minus. This is an equilibrium system, and equilibrium will be attained after some time at a given temperature. Now if you add acid H plus to it, if you make the solution acidic, H plus is added, immediately the process will move to the backward direction in order to restore the value of Kw. If you add OH minus 2e, immediately the process will move to the backward direction in order to restore the value of Kw. So Kw is 10 to the power minus 14, this equilibrium constant, this value will be restored even after addition of acid or base to it in water. That's why in aqueous medium, this Kw is always equal to 10 to the power minus 14 at a given temperature at 25 degrees centigrade. Now let us see if we apply this relation. For example, 0.01 molar HCl solution. It is given. So you know HCl is a strong electrolyte and you have to find the pH of the solution. You have to find the pH of the solution. So this is the concentration of the acid given. HCl dissociates fully into H plus and Cl minus. Understand? You have taken 0.01 molar HCl. So after dissociation, the concentration of hydrogen ion will be 0.01 molar and concentration of chloride ion will be 0.01 molar. But pH will depend upon hydrogen ion concentration. Therefore, hydrogen ion concentration equals to 0.01 molar. This is equal to 10 to the power minus 2 molar. So this is hydrogen ion concentration of HCl solution. Now pH equals to, if you write the pH negative log of this, negative log of this, negative log of 10 to the power minus 2. So see, pH equals to negative log of 10 to the power minus 2. This means this is equal to, so what is the pH? pH of 0.01 molar HCl solution is 2. See, the second example you see 0.01 molar H2SO4 solution. H2SO4 solution. In this case, you know that H2SO4 dissociates as 2H plus SO4 2 minus. SO4 2 minus. You have taken 0.01 molarity H2SO4. After dissociation 0.01, it will be hydrogen concentration will be 0.02 molar and sulfate ion concentration will be 0.01 molar, because the dissociation of sulfuric acid shows that every unit of sulfuric acid furnishes 2 hydrogen ions. Therefore, the concentration of hydrogen ions will be 0.02. Okay. Now, there you write that hydrogen ion concentration equals to 0.02 molar, that is 2 into 10 to the power minus 2 into 2 into 10 to the power minus 2 molar. So pH, if you find pH equals to minus log 2 into 10 to the power minus 2. This is equal to minus log 2 minus log 2 minus of log 10 to the power minus 2. This is equal to log 2 value 0.301 and this is log 2. So its pH will be 1.699. So the pH of 0.01 molar H2SO4 solution is 1.699. Sometimes we use very dilute acid, so dilute that pH of the acid is will never be, in terms of pH less than 7, the solution is acidic in nature. pH greater than 7, the solution is basic in nature. pH equals to 7, the solution is neutral in nature. So you know that pH plus pOH equals to 14 for aqueous medium. 14. So if pH is less than 7, then automatically its pOH will be greater than 7. pH less than 7, so less than 7 suppose 5 मान हो, 5 मानने से pOH कितना निकलेगा? 9 निकलेगा. That means greater than 7. And if pH is greater than 7, pOH will be less than 7. And if pH equals to 7, pOH will be equals to 7. So for acidic solution, pH is less than 7 or pOH is greater than 7. Both are right. 7 or pOH is less than 7. Both are for neutral solution pH equals to 7 and pOH is also equal to 7. That means a solution is acidic or basic or neutral. This can be expressed in terms of pH or in terms of pOH. Suppose the pOH of a solution is 4. So pOH 4, that means pOH is less than 7. So pOH is less than 7, the solution is basic. pOH is less than 7, that means solution is basic. तो pH के टर्म में या pOH के टर्म में किसी भी सॉल्यूशन को बताया जाए तो उसमें हम लोगों को एसिडिक और बेसिक नेचर हम लोग बता सकते हैं. Now see, suppose there is a solution of hydrochloric acid whose concentration is 10 to the power minus 8 molar HCl solution. So see, if you consider this solution, it is a very dilute solution of hydrochloric acid. Very dilute solution of hydrochloric acid. 10 to the power minus 8 molar. And if you find the pH of HCl solution, this solution, if you find this pH will come out as 8, but this can't be so. No solution, no acidic solution can have pH 8. What is the pH? pH of acidic solution less than 7. But what you find here? Greater than 7. Because the concentration is 10 to the power minus 8. 10 to the power minus 8 molarity HCl solution means it is very dilute HCl. Say you are adding just a few drops of hydrochloric acid in a water tank, full water tank. That solution will be acidic solution and having very less concentration, like 10 to the power minus 8 molarity. So such acidic solution, whatever be the strength, very dilute, pH will never be greater than 7, but it is 8. In order to clarify this, I am explaining this one. So, being a strong acid, its hydrogen ion concentration will be equal to 10 to the power minus 8 molarity. So, this 10 to the power minus 8 molarity, hydrogen ion concentration will come from HCl. In this case, when such type of values are given, you will consider the hydrogen ion concentration of water. Hydrogen ion concentration of water is equal to 10 to the power minus 7 molarity. So you see here, hydrogen ion concentration of water 10 to the power minus 7. This must be added to this because this one is added to water. So this must be added to it. Therefore, the net hydrogen ion concentration of the solution will be 10 to the power minus 7 plus 10 to the power minus 8. So see here, this plus this is equal to 10 to the power minus 7, taking common. So 1 plus 10 to the power minus 1, 0.1. So this is hydrogen ion concentration equals to 1.1 into 10 to the power minus 7. If you change it to negative logarithm of H plus concentration, this is equal to 7 minus log of 1.1. So this stands for pH. Therefore pH will be equal to 7 minus this, 7 minus 0.039 like this. So the value will be coming out as 6.961. Now see, it satisfies our condition, that is less than 7. So less than 7, that means the pH of such a dilute solution of hydrochloric acid will be 6.961. So now it is clear that in case of a very dilute solution, you will consider the hydrogen ion of water. This must be done in order to solve the problems. Now we have the concept of acid and base. Three concepts are there. Arrhenius concept of acid and base, Bronsted and Lowry concept of acid and base, and third one is Lewis concept of acid and base. So three: acid base, water acids, water bases, their definitions and their explanations are given by three concept. One is Arrhenius concept, another is Bronsted concept, and another is Lewis concept. This concept of acid and base will be discussed in the class itself. I am not doing any board work. It will be explained there. You will listen to me there in the class itself. Okay, boys. Thank you.
Last lecture. Class 11.
Class 11. It is your class 11, and I think this part, which part